All right. Hello, everyone. It's about 2 o'clock now, so we're going to kick things off. I'm sure some people will still be rolling in as we go here, but um, thank you for joining us today for the webinar. Hope everyone's doing well, staying safe, staying healthy. Uh, my name is Jeff Rossio. I'm the digital marketing manager for Harvey Performance Company. I'll be moderating today. And before we get started, just a few items that are of interest to people. It looks like a lot of you have already found the live chat, but if you have not yet, it should be on either the side of your screen on desktop or on the bottom on a mobile device. That's where you'll be able to communicate with us during the presentation. We do encourage you to insert any questions you have in the live chat. If there's something I can answer, I'll do my best to get it answered during the presentation. Otherwise, if there are questions better suited for our technical experts, I will save those for the end where we will have a Q&A and we'll go through all of your questions as best we can. This webinar is also being recorded and we can share it with you afterward if anyone's here who maybe has a customer or somebody who wasn't able to make the live stream. If you want that link, please just send an email to onlinemarketing@harveyperformance.com. We can send you a share link after the presentation. And so the presentation here should run about 45 minutes. We'll have about 15 minutes at the end for questions, and we'll get you all out of here in an hour. Don't want to take anybody's time too much, but should be about an hour here. And I will be back at the end of the presentation for the Q&A with Don Grandt, who's leading our presentation, and Reese Trotter, one of our application engineers who is also in the chat as well with me. So with that being said, I am going to pass it over to Don and let him take it away here.
Well, good afternoon, folks. Thanks for joining us. As Jeff said, my name is Don Grandt. I'm the National Application Engineer for the Harvey Performance Company. So with that being said, it's Thursday afternoon, 2 o'clock on the East Coast, and Central Time, I think it's 1 o'clock. So you know what we get to do today? We get to talk cutting tools. So I'm looking forward to it, and I'm happy you guys kind of joined us. And like Jeff said, if there's any questions, we'll kind of save them to the end. But what we're going to do is this session is actually cutting tools explained. So we're going to understand the benefits of tool geometries. And what this is going to include is we're going to talk about end mill anatomy and cutting geometry. We're going to kind of dive into it a little bit more. We're going to understand it a little bit better. We're going to then talk about end mill wear patterns. We're going to take a look at some end mill wear patterns. We're going to see what is causing some issues. We're going to maybe come up with some remedies, how to fix those issues, and then see if we can dive in a little bit deeper on that and make sure there's a better understanding to fix some problems right at the spindle. Then we're going to get into some drill point geometry. I'm actually an old school drill guy. So we're going to talk a little bit about drills. We're going to talk about some coolant. We're going to talk about how that drill point geometry affects what you're actually trying to get the efficiencies out of the holes you're actually making. We'll talk about some coolant benefits, and then we'll kind of wrap up with some tool holding and run out. So first, let's dive in with end mill anatomy. Let's see if we can't explain and understand a little bit more about an end mill and some of the features on an end mill and how they work. So first thing I want to talk about is the cutting diameter. The cutting diameter on an end mill is the measurement taken on the margin on the end of the flute, or 180 degrees apart. This is basically measured a lot easier with a micrometer, even flutes, but this will give you the diameter of the end mill that you're actually putting in your software. So if you measure it, all end mills come with a minus tolerance on them. So when you get an end mill, and let's say it's a half-inch end mill, industry standard on that end mill is going to be a -2 thou on that diameter. Some people run -1, but most end mills industry standard are going to be a -2 thou diameter. So if you get a half-inch end mill, expect it to probably be 499, 499.5. all the way down to 498 diameter is actually within tolerance. This is just something good to know when you're actually putting your tools in the spindle, that if you buy a 1/2 inch end mill, you're probably going to get it. It's going to be undersized, not by much, but it's always good to measure those diameters at the end of the tool, usually within the last 10% of that cutter diameter, just to make sure that your offsets are correct when you get started. Helix angle. So a helix angle is the angle formed between the center line of the tool and on the edge of the rake face. So all end mills come with different helix angles. Helix angle is very important to kind of talk about because it's kind of one of those things on an end mill that we look at and go, well, what's the difference? Do I have a slow helix? Do I have a fast helix? What's that angle, and how does that actually cause me to cut more efficiently or less efficiently? A good way to look at helix angle on an end mill is basically the slower the helix angle, or the more the helix angle is laid down, so it's more parallel to the center line of the tool, the stronger that tool is going to be. The stronger it's going to be, but the more force it's going to put on your wall. So the slower the helix, the more force. Think of it, it's going to push harder. It's going to be stronger, but it's going to push harder. The higher the helix angle, the less it's going to push on your wall, but the more it's going to pull down from your spindle. So as we're looking at helix angles, the slower the spiral, the more force you're going to put on your radial side. So think about that if you're running super alloys or alloys that are going to push back a little bit. You're probably going to get a little bit more deflection on your tool as that helix angle gets slower. As it gets higher, where it actually looks like there's more perpendicular to the cutting edge, that's where we're going to get the forces that are going to be up and down. So you're actually going to get a straighter wall as your helix angle gets higher. So if you're doing some finishing applications, if you really want to make sure that you get a straighter wall, depending on the material you're actually cutting, you really want to start taking a look at the helix angle. You might want to consult some of the experts, find out what the optimal helix angle is to put the less amount of force on that wall, so you get a straighter wall, you get a better finish. But you have to be mindful of how you're holding that tool, because it will want to pull out of the holder a little bit better. So that's kind of helix angles explained a little bit. The slower, the more force, the stronger it is, the higher helix, the better finish, the more pull-out force it's actually going to generate and create. Flutes. So if we take a look at the flutes in an end mill, the flutes are a spiraled cutting edge that create the helix angle that allows for chip evacuation. So the flutes are what's allowing the chip to actually evacuate the end mill. So these are created depending on the flute count that you have on the end mill. That's how your depth of your flutes are going to be calculated, depending on how many flutes are on that end mill. And it's going to allow the chip to have enough room to evacuate. So depending on what kind of tool path you're using, this is where we either want to have enough flutes for chip room, or we want to have enough flutes for strength. And if you look at the bottom picture that you can see on there, we can kind of take a look at flute numbers all the way from 2 to 12. So if you look on the left-hand side, if we're running 2 flutes, it's going to be number 1, conducive to the material we're actually cutting. That's number 1, is what material are we cutting? Because the gummier material and the low carbon material that we can cut freely can take a bigger chip, and therefore we're going to want less flutes. Less flutes is going to allow us with more chip room. Therefore, we can take a bigger cut and actually get the chips out of the flutes without having any kind of congestion. As the material gets harder, and as the material gets a little bit more difficult to cut, what we want to do is we want to strengthen up the core of the end mill, make the end mill stronger, but we're not going to be taking as aggressive radial step overs. We're not going to bury that cutter in there as we start running into super alloys or heat resistant alloys and stuff like that. So we want to increase the flute count in order to get a stronger core And we can limit the flute space because we don't need to take the radial step overs. So you can see from left to right, we have more chip room on the left-hand side. We have less chip room on the right-hand side, but we have a stronger core, which is going to give us more rigidity. Variable pitch end mills. So we have three different kind of geometries that we can add to end mills to break up the harmonics on an end mill. As an end mill wants to run, it starts creating a natural harmonic as RPMs start going up, and it wants to chatter and it wants to vibrate and it wants to get this normal resonant sound that creates a bad finish. Almost similar to driving down the road in a car and you have the knobbies on a tire and you can kind of hear that humming going, you get that reverberation of the tires, and end mill wants to do the same thing. So we have to break up those harmonics in order to get a freer cutting action and a better finish on the end mill. So there's three ways to actually do that. You can vary the pitch, which is basically the picture that you see on here where each one of the flutes is kind of broken up in a variation of the pitch. So instead of having all 90 degree on a 4 flute, what we'll do is we'll break up that pitch so you're not evenly or symmetrically broken up. So that end mill kind of has more of an odd number of flutes or an odd reverberation on the cutting edge, and therefore cuts a lot freer. That's number one. You can vary the pitch. Number two is you can vary the helix angle. We had the helix angle on there that we talked about before, is basically the angle of the flutes that are running up the center line. You can vary that. If you put 38 degrees on one flute, the next flute you can make it 36 degrees. The next flute you can make it 35 degrees. That's called variable helix. If you look at the Harvey tool catalog, we run variable helix on the Harvey tools. We run variable helix on Harvey tools all the way down to 8 thou in diameter, which I think is pretty impressive. So we run a variable helix on that. The other thing you can do is you can do a progressive helix, where you take the helix angle spread out for the length of cut on the end mill, and you start out at one helix. Let's say you start out at 36 degrees at the front, and by the time it gets to the back, it's 38 or 39 degrees. So there's three variations. You have variable pitch, where you variable the pitch of each one of the flutes. You have variable helix, where you can actually take the helix and change it from flute to flute to flute. And then you have progressive helix, where you can actually start out at one helix and then progress to another. A lot of end mill manufacturers can use any combination of these, and they can even add combinations to get the right geometry on their end mills. We have tested this at Helical and Harvey. We believe that what we do on the variable helix for the Harvey side on the micro tools really does a great job with breaking up the harmonics at the elevated RPMs on the micro tools, and then variable pitch on the helical side, which has been tested to show very good tool life and finishes for that as well. So we run a variable pitch on the helical side and a variable helix on the Harvey side. That can kind of get a little bit confusing, but all you need to know is that your end mill manufacturer is taking care of you, the end users, the distributor, to make sure that your tools are running successful in the spindle. That's really the nutshell of it. But it's good to understand what's being done there, as we're breaking up that symmetrical form of the end mills to break up that cutting action. Axial relief. So all end mills have relief on the OD of them to actually get them to cut, but they all have axial relief on the bottom of them too. So let's take a look at the end of an end mill. The axial relief is the relief behind the cutting teeth of a tool. It's on the outside of an end mill, it's on the bottom of the end mill. This prevents the tool from rubbing as it cuts. There's a primary and a secondary relief on there. On end mills, there's end cutting geometry on the end of the tool. This is for two reasons, right? It's for it doesn't rub on the bottom. That's number one. And number two, it's actually for it can be end cutting to plunge and for helical interpolation. If we didn't put relief on the end of it, it would rub, especially in helical interpolation as you're spiraling down to get to your bottom offset. So we put relief on a primary and a secondary. Even though end mills are not designed to drill or plunge because of the end cutting geometry and the gash angles and everything on the end, they're actually made to accommodate that function for the end mill. So you can plunge an end mill. I don't recommend plunging an end mill if you can helical interpolate, but you can do it with great success to certain depths. I would recommend if you're plunging an end mill, depending on the material you're actually cutting, I would always recommend a pec plunge versus just plunging straight down to a depth unless you're going shallow. But you can do a G81 pec and actually just get down to the bottom with an end mill the same way you could with a drill. But I would always recommend a pec because you will get stringier chips when you actually pec an end mill. Core diameter. We talked about core diameter. Core diameter is basically the diameter at the center of the end mill based on the flute count, number one. That's what kind of dictates the core diameter, is the flute count, or it can actually be designed and engineered into the tool. And what I mean by that is there are certain standards of a core diameter that you can put on an end mill that most companies use. But if you're designing a tool to do a certain function, whether it be a 4 flute, 5 flute, 6 flute, 7 flute, all the way up to 12 flutes, you can design that end mill with the proper core based on what tool path you're designing that tool for. And let me explain a little bit with that. Is you can take a 4 flute end mill that's going to give you a lot of chip room, and you can add a stronger core on that if it's going to be designed not to do full slotting. So you can design the core based on what the function of that end mill is to kind of start dialing your end mills in a little bit more to specific applications. So it's not just a standard core on a 4 flute, a standard core on a 5 flute, and a 6 and a 7. And I can attest that Helical Solutions has put a lot of design work in their cores based on their flute count for what kind of tool path you actually want to run with the tools. But as the flute count goes up, the flutes get shallower, so we have less chip room, but the core gets larger. So when you're looking at any kind of end mill, any tool to actually use, it really, really, and I want to stress this, and I probably should have said this right up front with all this anatomy we're talking on end mills, it really is conducive to the tool path you're running with your end mill. I'm a national application engineer. We have some local application engineers. One of our first questions we're going to ask anybody that wants a suggestion for an end mill is, what tool path are you running? Is it high efficiency? Is it traditional? What type of tool path are you using so we can fit the right flute count, the right core diameter, the right length of cut to give maximum rigidity of that tool for that application? That's number one, right? What tool path are you running? Very critical. Number two, anybody want to guess what number two is? Well, you can't comment, so I'm going to tell you. Number two is actually the material you're actually cutting, right? What material is that? Because we can take, here's a good example, and I'll throw out these little examples. So a 7 flute tool is going to cut really fast with an HEM application in most super alloys. Would I suggest a 7 flute end mill for a 1018 cold roll material? I wouldn't. The material is softer. It's going to make a bigger chip. We can feed it faster. So now you can run an HEM application with a 4 or 5 flute in a cold roll material, whereas I wouldn't even want to put a 7 flute in there because I'll probably start gumming up my flutes a little bit faster. Even though I could get maximum cycle time out of it with a 7 flute, I don't think I would last as long because I would get a built-up edge because I couldn't evacuate the chips. So it really is conducive, flute count or strength, to the material you're actually running and the tool path you're putting that in. Very important when you're picking out an end mill with helix angles and core strength and flute count is what tool path am I using and what material am I cutting? That is very important to kind of understand before you start diving into your end mills. Then we can talk about coatings, we can talk about length of cut, we can talk about helix angles and everything else. A lot going into an end mill, a lot of design work. End gash. So in order to get the center cutting on the end of the tool, we have to gash it. The gash is what's there to actually give you the chip evacuation on the end of the tool. We go in, we design, we engineer the gash, we make sure that the gash angles, the opening, the radius is built for a bunch of things. It's built for strength, it's built for chip evacuation, and again, it's built for the function of the flute count and the core strength of that tool. Very important. Again, a lot of engineering goes into the cutting tool to make sure it cuts the right material with the right tool path. So it is very important to, when you're looking at an end mill, to pick out the right geometry and right specs for that application. Oh yeah, there's my real fancy, that's my only animation I got going on this there. If you guys want to see it again, I can back up. That's an end mill. It's got a little bit of a TIR issue with it, but still nevertheless. Radial relief. So we talked about the relief on the end of the tool that actually gets relief for it doesn't rub. So there's radial relief on the outside of an end mill. One of the most important features of an end mill for material specific end mills, that radial relief can be defined and actually ground in 3 different methods on an end mill. Each method has its own pluses and minuses. The first one is a cylindrical relief, okay? A cylindrical relief is basically where it has a margin on the end of the end mill, if you look at the left-hand side, that has 0 relief in it. It's a very small margin, but it has 0 relief in it. Then there's a primary relief behind it and a secondary relief behind that. The reason there is a cylindrical margin on certain tools, again, based on material, usually softer material, is because it will not grab, it will stabilize the cutting edge, it'll give you a better finish, and it'll be stronger, especially for a lot of aluminum applications. There's a little cylindrical margin on the end of the tool to help stabilize that tool. That's number 1. Number 2 is an eccentric relief on there. Eccentric relief, when you think eccentric relief on an end mill, think built for strength. That is built for strength. Any end mill that has eccentric relief gives a lot of strength behind the cutting edge. It's not a flat grind, so it gradually rolls off the face of the tool and puts as much strength behind that cutting edge as possible. The downside with eccentric relief versus a flat grind or a standard that you see on the right-hand side is you might tend to rub a little bit more than if you have a flat grind relief, because it doesn't roll as much as a flat grind. So it has more of a gradual relief because we're putting strength behind that cutting edge. So if you're running your titaniums, your super alloys, your Inconels, your pH material, your 13H, your 17.4s, eccentric relief is really the way to go to give you the best tool life. The last one is standard relief. Standard relief is kind of, I like to call it, old school end mill technology. And a lot of people that are reconditioning your end mills that are standard grind shops are probably putting standard grind relief on your end mills when they send them out. Now what this is basically a cup wheel that's putting a flat grind primary and a flat grind secondary. So they're a little bit more aggressive than eccentric relief. They don't put as much strength on the cutting edge. This is just from history, and they've been doing flat grind relief from, the 40s all the way up. It'll put a lot more chatter on the cutting edge. The coating doesn't adhere as good, but it is still an effective grind that you can actually put on your end mills, flat grind. So there's 3 reliefs: cylindrical relief, which is basically for your softer materials, your aluminums, your non-ferrous; eccentric relief, which gives you the biggest strength behind the cutting edge that you're going to want to kind of make sure any end mill you're using for especially Inconels and super alloys has eccentric relief. And then standard flat grind relief which is probably what, like I said, you're getting from a local grinder, or maybe a general purpose end mill would have more of a flat grind relief. Anything you usually see with a flat grind relief probably doesn't have variable pitch or variable helix as well. So that's just something to keep in mind if you see flat grind relief. Usually doesn't have variable helix or variable pitch. Let's talk about end mill wear patterns. This is very important. This is probably some of the meat and potatoes behind some of the things you guys might be seeing out in the field, and how do I address some of these issues. So tool wear is kind of broken down to 4 different areas on an end mill, right? We have chipping, thermal cracking, fracturing, and then a standard wear land. We're going to start by talking about a wear land. So if you think about a wear land on an end mill is actually not a bad thing if it's wearing correctly. That's your first sign of something happening to your end mill. So usually a wear land is a pattern of uniform abrasion along the cutting edge. So this is where you're looking at the cutting edge. You don't see any chipping. You see a uniformed or a shiny spot down the cutting edge. Now I'm going to dive into this a little bit more because I don't want to really call a wear land a problem with the end mill, because all end mills are going to wear. That's what they're going to do. What we're looking for is, when is that wear land becoming excessive? When is it happening too soon? And how do we fix it when it's happening too soon? Okay, so your causes of that are usually the materials, the mechanical abrasions, but what we're looking for is an even wear land on the cutting edge. But you will see this probably within a couple cuts when you first put the end mill in. I like to say an end mill is only new once, and it's new when you put it in the spindle. After you make the first cut, it's not new anymore. So you're going to get wear on that tool, just like you would on a tire on a car. It's going to get wear on it. The second thing we're going to talk about is chipping, right? So we get chipping on an end mill. Chipping can be identified by a nick or a flaked edge on the cutting tool or on the surface finish of a part. You can see it. We use an end mill. You look at the surface finish on a part, you see a little line going through that. That's usually a chip or a nick on the cutting edge of that tool that's putting that line in there, okay? These are microchipping promotes irregular wear and bad surface finish. Microchipping can lead to catastrophic tool failure. If you chip a cutting edge, usually if there's a coating on the end mill, you're starting to get beyond the coating. So if it chips, you're pretty close to getting to catastrophic failure. So we're trying to eliminate the chipping. So some of the causes for chipping, because I know this is a common problem with a lot of end mills, can be caused by excessive loads in the metal cutting operation and thermal cracking. That's just a small, very, very small snippet of what can be causing chipping of your cutting edge. We're talking about end mills. This whole session is basically on end mills. If we were talking about all the causes, we could be on here for 3 or 4 hours, because a lot of the issues for chipping is going to be your holder, your machine rigidity, your fixturing, your toe clamps, your hangout. There's so many factors that can cause chipping on an end mill. But if we're just looking and your setup is ideal, let's look at some of the remedies for chipping. It's due to pressure. Part of the things that happen when you get chipping on there, it's due to pressure. Pressure is actually caused by chip load. Chip load is by your feed of your end mill. So if you are getting chipping on your end mill and you've eliminated most of the usual suspects, run out, holder, fixturing, vibration, all that stuff, what you want to do is slow down your feed. That's what I would tell you, is you're feeding a little bit too aggressively with that end mill if you picked out the right geometry and you want to slow down your feed. So chipping is kind of conducive to vibration, too much of a load, too much of a force on that cutting edge, so slow down that feed on there. Also, and this is where I like this presentation because it all kind of comes together a little bit. If you're chipping on the end mill, on the end of the tool, or on all the way up the cutting edge, look at that relief grind on the outside and see if it's a flat grind relief or if it's an eccentric relief. Because if it's a flat ground relief end mill, it's going to be more prone to chipping on that cutting edge. Remember the slide I showed you guys before? The flat grind relief is not going to add as much strength. So it might be time, depending on what you're cutting, to take a look at that end mill and maybe find out if that's flat grind relief and go to an end mill with eccentric relief, just to give more strength behind the cutting edge. But 9 out of 10 times, if you're chipping on the cutting edge, I'm going to look at that tool. If everything looks all right, first thing we're going to do is start reducing the feed on there. Thermal cracking. Let's talk about thermal cracking. Thermal cracking and milling cracks perpendicular to the cutting edge, and most common types of thermal crack are most common types of thermal cracking. These cracks propagate slowly and lead to accelerated wear and chipping. So what's the biggest cause of thermal cracking? Ineffective coolant applications are always a huge problem with carbide and thermal cracking. Now, I have an opinion on that. Number one is we're going to want a coating on the tool depending on what you're cutting, because thermal cracking is going to come from heat. And if you have heat at your cutting edge and you have heat in your end mill, it's probably because you're running in a material that pushes heat into your end mill. So if you have any kind of material that's going to cause thermal cracking, you should be using an end mill with coating. So one of those remedies, the first thing that says add coating, that would kind of be an assumption that if you're going to have a problem with thermal cracking, you probably should have a coating on there. Number two is reduce the feed rate. And then number three, remove coolant or run dry. So remember I said I have an opinion on this. We all have opinions on this. Opinions are always based on experience. I like to give my opinion based on experience, and I'm sure we have a lot of experience and different experience on this call today, and people might agree or not necessarily disagree, but maybe have different results with different materials and things. So as we start getting into different tool paths, mainly HEM, high efficiency machining, which we are, me and Jeff are working on a presentation that really dives into high efficiency machining that we're going to present if this one goes really well. But as you start getting into high efficiency tool paths, you're really starting to take the heat out of the point of contact. That's the point behind high efficiency machining. So the point I'm trying to get to is every time I run HEM tool paths, depending on what material I'm running, I always have better results running with coolant. I get a lot of questions out in the field. I get a lot of questions on these things. Hey, do I run dry? Do I run with coolant? What's better? I hear you're supposed to run dry to activate the coating. I hear you're supposed to run dry with this material. I have run high efficiency tool paths over and over again, different machines, different programs, different tool paths, different cam packages. I always personally have better success running with coolant and high efficiency tool paths. Just my opinion. It's mixed results. I'm sure everybody runs a little bit different. Just giving you my opinion there. I run better without coolant. Now, when you're running traditional tool paths generate a lot more heat. They really do. They're a heavier radial step over. You're in the material a little bit longer. They generate a lot more heat. All that goes out the window. Be careful for thermal cracking, okay? Because you don't want to douse a bunch of coolant on there, especially if your lines aren't perfect, and get that thermal cracking. So high efficiency machining, my opinion, run with coolant. Traditional tool paths, be mindful of the coolant. Use coolant where you can, but be mindful that you're not bringing coolant in and out to get the thermal cracking on there to induce premature wear and ultimately sacrificing your tool. Fracturing. Fracturing is kind of a byproduct of chipping. Causes the same thing basically in chipping as speeds and feeds. Too much pressure on the cutting tool, too much hangout. You want to reduce your speed, want to reduce your feed, you want to reduce your depths of cut. Catastrophic failure is fracturing. I don't want to stay on that one too much because it's pretty obvious. If your tool breaks, we have to reevaluate the application. And that's a big thing with me is if you're having common wear on an end mill and it's a helical tool, or maybe it's one of our competitor tools. I've gone into a lot of situations where they've had 5 different brands of tools at the spindle, and they're like, this keeps breaking my end mills. The end of my tool is always breaking. It's always breaking, and there's 5 different brands there. Well, at that point, it's not an end mill issue anymore. It's an application issue. We really got to start diving into the application. We got to find out what's causing that problem, and we got to correct it. In which case, the first end mill you used, in most cases, hopefully it's a helical solutions end mill, a Harvey tool, or a micro 100 one. But odds are you'll have better success with any one of them. But that's my sales pitch for the whole one. But if it is the tool that you have in there, the one that was recommended, the application has to be conducive to the end mill that's actually been selected for that. That's very important. We're willing to help. We have great application engineers. I'm sure there's other vendors as well with a lot of experience, but we're more than happy to dissect those problems and help you walk through it. Okay, we're gonna rock it. Yeah. So see, you get me talking about cutting tools, man. We could do this all day. I'll offline. Anybody want to call me up? I'll give out my cell number. Oh, so there's 2 types of stresses, and then this is about the end of this anyway. As far as tool wear goes, there's 2 types of stresses. There's thermal stress and there's mechanical stress. Thermal stress is basically those inconsistencies, the work hardening, how much heat you're putting in there, the rubbing, too much surface foot, not enough speed, rubbing, generating that heat and getting those cracks in the end mill and premature wear. Mechanical stresses are the stresses that come in from the machine, the abrasion, the vibration, ship congestion, wrong flute count, built up edge, suspect tool holding or work holding, unmanageable metal removal rates where you're just pushing the end mill too much. So there's mechanical stresses and thermal stresses that we're actually trying to eliminate. These are things we're trying to eliminate. So remember we talked at the beginning of this, a tool wear. There's really 3 patterns of an end mill. There's initial wear pattern, there's an intermediate wear pattern, and then there's a completion period. If you look at the bottom, all you really need to kind of understand is on the left-hand side, you're going to see a wear pattern. You want it to be even. You want to have a nice even wear on there. On the right-hand side, you can see the bad is where you're getting fracturing, chipping, and those type of things. As that wear land goes through a metamorphosis, as it's rubbing against the material, whether it be abrasive material, whether it be non-abrasive material, it's going to wear your cutting edge. That's why it's important to start out with the best geometry and then manage the tool all the way through its period until you either want to recondition it or throw it in the garbage. 2 things. Recondition it, you want to pull it out at the right time. You want to monitor your tool wear. If you're just going to pitch the tool, then it could be to a point where it breaks. Those are the things you want to watch, but it's going to go through a metamorphosis as it starts out with brand new all the way to where it's chipping. Monitor it, find out what an adequate tool life is for you. It's not about the cost of the end mill. It's about the cost of the cut. It's about the cost of the pass. It's about the cost of the job, not the cost of the end mill, not the cost of the drill. It's not the cost of the drill. It's the cost of the hole, right? It's not the cost of that. That's what we're actually trying to make sure we're getting maximum tool life. So I put this together real quick on drill point geometry. Like I said, I grew up in a drill manufacturer environment. I grew up in the point geometry. I was an engineer for a long time. If you're using a drill, the most important part of a drill is the point geometry on there. There's some features on the end of the drill that's very critical. A chisel edge that's straight down the middle of it. There's a chisel angle on the end of it. There's a cutting edge that actually creates the swarf or the material that actually cuts, but your chisel edge is doing a lot of the work. And then there's a rake angle and a clearance on the end of the tool. All again designed for certain materials, for certain applications, for certain operations you're actually running. So let's take a look at the drill point. The drill point's the working end of the tool, right? The chisel edge is the first point of contact that actually hits the material. And you guys are going to see this is going to kind of accumulate to one slide that I'm trying to stress here. The chisel edge creates the majority of the thrust force. So as your drill is drilling down into the material, that chisel edge is creating how much force is pushed up on that drill into your spindle. The more force that's pushed into the drill, the less effective it's going to be, the more it's going to walk, and the more catastrophic failure you're going to have. The chisel edge angle is its accuracy along the alignment of the cutting lips, controls the positioning, size, and straightness. So depending on how much that's running out, how accurate it's ground, that's what's going to control your hole size. So the correct selection of point geometry is paramount importance to the tool performance. Again, drill point controls the chip formation, controls the size and shape of the chips. The drill point does. That's what's doing it. The rest of it, believe it or not, the flutes on a drill are just evacuating the chips. You're making the chips with the point. You're cutting the material with the point. The flutes are there to evacuate the chips. Controls the hole size and quality, controls the size and amount of burrs produced depending on the material, burrs at entry, burrs at exit. That drill point's controlling all that. Increased strength of the cutting lips, reduces cutting lip wear, reduces amount of heat generation. Drill point, very important. Can you tell I'm a drill point guy anyway? So let's take a look at this real quick. This is a really good depiction of this, okay? High thrust forces. A chisel of 10% of the diameter of a drill, 10% of the diameter creates 70% of the force of that drill. So if you have 10% of the diameter on a half-inch drill, it's creating 70% of the force of that. So if we look at 70% of the force at 10% of the diameter, and we thin the web, let's say we thin that down to 2% or web thin. Look at what happens. We reduce 40% of the thrust force on that drill. 40% by thinning that web. So what's the point, Don? The point is, number one, always choose a drill for the material that you're actually cutting, material specific. You can apply this to carbide drills. You can apply this to standard high-speed steel drills, cobalt drills. A lot of them don't come with a web thin in there. If you thin the web or grab a drill with a split point that's usually 2% or 3 to 5 thou on the web, you are reducing the drill force by 40% on that tool. When you reduce the force on the drill, you get a straighter hole, you get less vibration, you get better self-centering, and you get a rounder, smoother hole and better tool life. So 140-degree split point on a drill, special purpose application, reduces the thrust force, number one, by 40%. More manageable chip formations. Now you have two different cutting edges on there. So you're literally taking the other ones and breaking the chip into two different formations. So you're managing the chip a lot better with a split pointed drill on the end of it, or a gas drill, or a web thin drill. And your improved centering ability. It self-centers the drill. Instead of having that big, long, thick chisel edge, you are self-centering the drill and you get faster penetration rates. You can run a lot faster. So let's talk about the coolant benefits to a drill, and then we'll throw in some end mill benefits too as well. A lot of people don't realize that the coolant benefits are not just what coolant stands for, which means cooling, right? It's not just cooling. Some of the coolant benefits actually provide three different advantages by using coolant. Number one, you assist with chip evacuation. That's huge, right? As you're running coolant, you're actually blowing the chips away from the action of where you're cutting. So number one, and I would say almost most important when you're running with an end mill or a drill, is you're moving the chips out with your coolant flow. That's number one. Number two, provides lubricity at the cutting edge. Coolant provides lubricity. It's not just cooling the cutting edge. It has emulsifiers in it and different lubricants to actually provide lubricity so chips slide off the cutting edge better. And number three, offers heat dissipation, right? So there's three advantages to coolant. Remember when I said, should you run dry or wet? I'm a coolant guy. I know there's a lot of companies out there that are trying to push people toward dry machining. It is a lot cleaner on your machine, saves you some money, but I'm telling you, the long haul for saving money, in my opinion, with cutting tool life is by using coolant. So we have coolant options, right? Good is kind of a missed option. So that missed option right there isn't going to do you a lot of good for evacuating chips, but it is going to provide lubricity and a little bit of cooling. Not as much cooling. Better is going to get more of a flood system. That's going to provide a little bit more chip evacuation, more coolant, more lubricity. And of course, the best when you're using a drill is coolant through drills, that you can actually push the coolant all the way down through the cutting edge at the point of contact. Hey, and where's the coolant coming out? Coming out at the point, right? The point is the critical part of the drill. That's where the coolant comes out. That's where the chip is made. That's what we're trying to control. That's how we're trying to help break the chips out. Tool holding and run out. We're going to close with this really similar, or just to kind of recap with everything, because if you have bad tool holding and run out, all those things we talk about, the chipping, the wear patterns, the edge, the maintaining tool life, all that is pretty much a moot point before you even get started, okay? You need to use the right holder. That's number one, the right holder for the application you're running. You need to keep the holders clean and in good shape. Always critical. You spend a lot of money on good holders. It's important to keep them clean and in good shape. Also, if you're using coolant in your machine, which I do recommend, make sure your concentration is correct so we're not rusting out our holders. Really cause some damage. Don't maximize ER collets. Let me explain what I mean by that. If you have a 1/4 inch end mill or a 1/4 inch tool, do not put a 9/32 collet in there. Will it work? Will a 9/32 collet close down on a 1/4 inch end mill? Everybody that's probably on this call is going to say, yes, it will. Will it do it several times? Probably not. You're going to damage the collet, number one. Number two is your run out is going to be all over the map. So it will hold it, it will work, it'll cut, but it is not the ideal way. And you're going to basically throw away the cost of the end mill with the collet damage that you're actually going to cause. Very critical to make sure your collets, your holders are in good shape. Check for cracked collets and nuts, and make sure you have the correct pull stud. And then the pull stud's in really good shape. If you look at the graph I have down here on the right, and if you notice, I picked up my pace. I'm talking really fast. I'm a fast talker to begin with, so, you know. So if you notice the slide down at the right, this is a concentricity as the feed per tooth TIR gets out. As a tool run out reaches 50% of the feed per tooth, which means if I'm feeding 3 thou inch per tooth and I'm at 1.5 thou run out, I am losing 65 to 85% of the tool life right out of the gate. 65 to 85% just by having 50% of the run out of the feed per tooth. Very critical. All of our end mills run 2/10. 2/10 is what you should be looking at for max run out on the end mill. So if the end mill is running out more than 2/10, check your holder, check your collet, check your fixturing, make sure that you have the right stuff. Get with your tool supplier, make sure you get the right collets. I'm telling you, if you put the right holder in there, you will save money long run. There's a huge cost savings, and your productivity, your finishes, your wall straightnesses will be much better. Lower run out lowers tool life, decreases part finish. For every 1/10 run out, 10% tool life. You don't want to, you want to make sure you have the right amount of shank up in the holder. It's critical. There are a lot of fixturing issues, obstacles that we're trying to overcome. It is important to make sure you grab the right end mill with the right OAL, right length on it, not the cutting length, but the right overall length to make sure that we have optimal shank up in the collet. Usually 3 times diameter is optimal. You want to make sure that you have the right holder in there, because I can tell you right now, you will get run out by having 1 or 2 times D in that collet. That collet wants to clamp across the whole surface. If you don't put it all the way up in the collet, the hydraulic holder, it will deflect. It will push it off to one side. You'll have run out issues, and you will have problems with that. So I understand that you're trying to get over obstructions and toe clamps and things like that, but it's very important to make sure you have the right shank up in the holder. That's it for me, Jeff. I just wanted to turn it over. I thank everybody for their time. We're always available. We have a great tech team at Harvey Performance. We have great, really good friends of mine, very smart, intelligent application engineers that have come from shops that know their stuff in everybody's territory. Reese Trotter is actually up in Minnesota. I know this is kind of geared toward that. Reese is an incredible, smart application engineer, and he can pay me after this. But we do have a lot of great people to help with applications. We're more than happy to suggest tools and back them up. That's the biggest thing, I think, when you're working with an application engineer. They got to back it up. And any one of our guys in the field will stand right next to you, right next to the machine, and push the cycle start button. So with that being said, if there's any questions, let's get to it. Yes, sir. Yep.
All right, everyone. So thank you, Don. That was another excellent presentation here. We do have a few questions coming in. Before we get to those, we're going to call Reese Trotter, the application engineer that Don just mentioned for the Minnesota area. We're going to call him in here so he can answer a few of these questions as well. In the meantime, if there are any more questions, I do see a few in the chat that we're going to get to, but please feel free to throw them in the chat right now. And this would be a great time for Don and Reese to jump on some of them. So, do we have Reese?
Yeah, I'm on here, guys.
All right. So, that was Reese Trotter, application engineer, and so one of the first questions for you guys: what about RPMs, and how does that affect tool wear? Don, I think your mic is muted.
How about now, guys? You got me. There you go.
Gotcha.
I'm sorry. I'll take that one, Reese. So RPM is very, very critical because RPM is what's generating the heat at the cutting edge, okay? RPM is directly related to surface footage. Your surface footage is basically recommended for the tool path you're running, just like we talked about. We're going to ask what your tool path is, number one. We're going to find out what your material is, and then we're going to dial in your surface foot to give the right RPM with those radial axial step overs to generate the right heat at the cutting edge. So I can give you a little tip on RPM to say, if you are running a tool and you are not getting the tool life out of that tool and it is not chipping, usually what you can do is feed it faster, okay? That's number one. Now, if you're chipping on the tool, if the tool is chipping, okay, I talked about slowing down the feed. If it's chipping, what you can do is increase the speed so as you don't lose your MRR rate. Sometimes we will do that. The last thing that we want to do as a company and as you want to do as a vendor is to slow down your machine. So what you can do is increase your RPM if you're getting tool failure from chipping and not from rubbing and wearing.
Awesome. Thanks, Don. So one more question we have from Ryan here. How do you guys decide what or whose end mill to run, owning the three different companies? Obviously, we have Micro 100, Harvey Tool, Helical, and Ryan nicely said, Micro 100 has some killer end mills, but Helical does as well. So how do you kind of decide when you go into a shop which one of those you're going to approach with?
Okay, this is a great question. And I've had this question before, actually at John Deere in a big meeting. And there's a real easy answer to this. First thing, number one is it's great having all three brands because there's not too many problems we can't solve because every one of the geometries with all three brands are a little bit different. Helical does a variable pitch. Harvey has a variable helix. Harvey offers some helix angles that are a little bit different than helical. Micro 100 offers some odd diameters and lengths of cuts that helical and Harvey don't offer, okay? So what we really do is our main goal is to fix the customer's application problem. Having 3 brands, 3 companies, 3 different variations of geometries, variable helix, variable pitch, allows us to really find the right tool with the right vendor to put the right tool in there and solve the customer's problem. So to answer your question, they're all just a little bit different in the way they manufacture the geometries that are on them, that we can really pick the right tool for the right application.
Awesome.
Yeah, I agree with that, guys. With Micro 100 as well, I mean, between the differences, another thing is flute counts as well. Depending on what material that we're running in with the different coatings, which combination kind of would align best with the application. So it's hard to really say which one you would go with when there's so many different options.
Awesome. Thanks, guys. Let's see, one more question, and I can actually answer this one, but somebody asked if a copy of this would be available. And yes, we can get you a copy of this presentation. Just shoot an email over to onlinemarketing@harveyperformance.com, and I will make sure to get that out to you shortly. We should be able to have it pretty quickly after this ends. So if you're interested and want to share it with people, I can make that happen for you. Other than that, it doesn't look like there's any other questions in the chat. I'll give another minute here to see if anybody wants to throw anything in and get a question while you have Don and Reese here on the call. But otherwise, just so you guys know, Don and Reese, lots of thank yous and great jobs coming in. So props to you guys on putting together the presentation, and lots of good reviews here.
Hey, Jeff, I just want to throw out one more thing to everybody out there. Number one is, Harvey Performance is 100% fully operational and up and running through this crisis. I know it's hard out there at this point, but I also want to throw out there that we do have a little bit more time available. We all do. So this might not be a bad time if anybody has any application opportunities to really dive in and fix some things out there, or when this, because I'm a firm believer that this is going to come back tenfold and it's going to hit hard. And if we wait until then to start sharpening our pencil and making sure we have the right end mills, we're available now to give a little bit extra attention and look at those applications and really dive in with the right tools and get the most when this comes back. So I just kind of wanted to point that out, that Harvey Performance is up, fully operational, and we're ready to go. So if there's anything that comes up, we're more than happy to jump on it for them.
Awesome. So a couple last second questions came in here. One from Tyler. This is a little bit outside of our ball game, but I'm sure one of you guys can answer this. Just wanted to ask about ER versus SK holders.
Okay, absolutely. This is not outside my realm, because I have 4 SK holders sitting in my office right now.
I should have known.
So this is great. So I'll start out with the differences of the two, and then I'll tell you the suggestion. So the differences of the two is an ER collet has a larger taper on the end of it. It's like a 12-degree taper on a SK holder. So your surface contact on an SK holder is a lot greater than it is on an ER collet. An SK also has a pilot on the end of the collet that centers itself into the actual holder. So when you tighten down the nut on an SK holder, it won't naturally move the collet left or right. An ER holder, possibly if you over tighten, because it doesn't have a pilot on it, can shift the collet left or right and give you bad TAR. So that being said, SK holders we use for HEM, high efficiency machining. I think they're one of the best high precision collet systems in the market. I use them. I test with them. They're really good holders. ER holders are a little bit more general purpose. Good holders. They're not bad depending on what you're doing. But if you really want to step up your game, go and stick with the collet game, SK would be the way to go.
Awesome. And another question from Ryan. He's curious about left-hand end mills versus left-hand helix with right-hand cut.
Yeah, so left-hand end. So we have two kinds of end mills. We have left-hand end mills, and then we have left-hand helix, right-hand cut end mills. Okay, so both used for different applications. We don't see a lot of left-hand end mills because of the way you can fixture your parts. It's a little bit different. You know, anytime you need a left-hand end mill, you can kind of cut from the other side of your material and not need it. Okay, left-hand spiral, right-hand cut is a different purpose. Left-hand spiral is basically going to help you from pulling your material off your table. It's going to help keep everything down, but yet still run an MO3 code, you know, still run a clockwise code. So it's still going to spin right hand, but it's not going to have that lifting force on a left-hand spiral, right-hand cut. A left-hand end mill is an entirely different approach that you need to take to your material. It's coming in from a different end. It's pushing your material to a different force, but it's still going to pull up on your material. Left-hand spiral, right-hand cut will not pull up on your material. It'll push it down. Harvey Performance has left-hand spiral, right-hand cut plastic cutters for a lot of vacuum tables and stuff like that, and that's the reason for it. And you can actually use it on ferrous materials too if you're not holding on to a lot in your vise.
Awesome. So I think that's about it. That's about all the questions. Lots of thank yous and praise for what you guys put together. But thank you to everyone out there who tuned in and spent the time. Hoping to do more of these in the future since we're all kind of living with this new normal and trying to figure things out from different locations and doing things digitally. And hopefully you all enjoyed it and we can do this again. So, and yes, we can get copies of the presentation out to everybody. Quick question here that just came in. Do you stock for titanium and micro sizes under 1/8 inch?
Yes, sir. Exotic end mills down to 0.2 millimeter for titanium. 0.2, yep, you heard me right. 0.2 millimeter, that's 0.0078 thousandths of an inch. Variable helix, exotics, the yellow section in the Harvey catalog, all different sizes, corner rads, all the way down to 0.2 millimeter for titanium materials.
Yep, and Ryan, if you need any help, you know, with the tool selection on that, you know, feel free to reach out to us. Our customer service and tech teams are still running, and all our application engineers are still out there working. So just let us know. But I think that's about it. We're gonna sign off here. So thank you everyone for watching and listening and tuning in. And hopefully we'll have some more coming your way soon.
Appreciate it, guys. Thank you.